what you can learn about here is what's called the formal charge. Now this is different than oxidation state. When we look at oxidation states, we assume that if we have one element more electronegative than the other element, there is 100% capture of electrons by the more electronegative element. So we have something like oxygen, hydrogen. Oxygen is going to take all the electrons away from hydrogen it can for its bond. What a formal charge does, it assumes that instead of having a completely ionic bond, we have a completely covalent bond. So let's look at water again. When you look at water, and we do the total accounting, we draw a circle around. Oxygen starts out with 6 electrons. We have 4 lone pair electrons. And if we start at the top, work our way around, oxygen gets 2 electrons from this oxygen-hydrogen bond. Continue moving around, we get another 2 electrons from the oxygen-hydrogen bond, and we end up with a -2 oxidation state. Now, the formal charge is going to look similar to the total accounting. But instead of subtracting out 2 or 1 or 0, depending on whether or not we have more electronegativity or less electronegativity or an element bound to itself, we're only going to subtract out 1 for each bond. So this is your oxidation state up here, which is a -2. Your formal charge is, again, the number of valence electrons minus the number of lone pair electrons. But this time when we work our way around, when we start up here and we hit our first bond, we only subtract off 1. Because we're going to assume that this is a purely covalent bond. Oxygen and hydrogen are each sharing electrons equally, so they can only get 1 electron back out of the bond. We continue around, and once again subtract off another 1 for the next oxygen-hydrogen bond. This will give us a formal charge of 0. So what do formal charges tell us? Well, the oxidation state is one extreme, purely ionic, and the formal charge is the other extreme, completely covalent. So what this tells us then is that if we look at the true oxidation state of oxygen, it's going to be somewhere between -2 and 0. And where that actually lies depends on actually doing quantum mechanics calculations. It requires a much higher level of theory. But what it says is that between these two extremes, purely ionic and purely covalent, that's probably where the oxidation state really lies. So let's take a look at another one. Let's look at methane, CH4. So CH4, when we do our total accounting, carbon starts out with 4 valence electrons. We draw our circle around. We'll start here at the top. As we move away along, we subtract off 2 for the carbon-hydrogen bond here, 2 here, 2 here, 2 here. And this will give us a -4 oxidation state. Now if we're looking at the formal charge, again, we're going to start out with the 4. We don't have any lone pairs. And now every time we hit a bond, we're going to subtract off 1. So we have 1, 2, 3, 4. So what that tells us then is that the actual charge on carbon lies somewhere between -4 and 0. In the case of carbon and hydrogen, it's much more likely it's closer towards 0 than it is towards -4, because these aren't radically different electronegativities we're working. And that's the idea of formal charge. It represents the other extreme. Instead of looking at bonding in terms of completely ionic, you're now going to look at it as completely covalent.